this is the talk about recent work on extending the Virtio specification. You see the title, and the first surprise is I'm not Michael Zirkin. So he couldn't make it. His flight was canceled last minute. My name is Freimann. I work with him on the same team. I've been working on the new Virtio ring layout for the past couple of months, and I'm filling in for Michael today. So this really is his presentation. Okay, so the goal with extending Virtio is on improving its performance. We want to make it a better fit for new workloads, and currently the support for that is not well. So there were several underlying assumptions from when Virtio was during its early stages of its design. We looked at them again, and some of those results were surprising. So there are also some common misconceptions or misunderstandings about Virtio, how to work with it or how to extend it. We're going to talk about this as well today. Before I go into this, we need a little bit more background about how the current Virtio is working. So during this talk, I will mention a lot, we will add a new feature bit, or this needs a new feature bit. And what this means, we'll talk about first. Then we can continue with other stuff. So let's go about the initialization of a VM with respect to Virtio. So every device has a device ID, right? And ID 1 is for network, ID 2 is for block, and so on and so on. The guest OS, it uses this ID to load the correct driver for a Virtio device. Each Virtio device has 2 bitmap registers, and collectively we call them feature bits. So one of them is called the device features. The other one is the driver features. And then there's also a status register. And they reside somewhere in shared memory, and in the device and in the driver memory. So at the moment, they're both 64-bit registers, but they're easy enough to extend. So here's how they're used. The driver will start by reading the device features, and a copy of it is loaded into VM memory. Built into the driver is a mask of supported features. And that's really just a copy of the device features recorded when the driver was developed. The job of the driver now is to do a bitwise AND of the device and driver features in VM memory. The result is then used by the driver to determine how to drive the device, what features can be used, what can't be used, what does it support, and what not. And this is also written into the driver features register on the device. So both know what the other side supports. At this point, the device can validate the feature register value, and if it is valid, it can set the status register features OK bit. If not, then this bit will be cleared. This means the driver can check the status, and it can either start using the device or it will fail gracefully and give a warning to the user. Okay, with this out of the way, let's talk about the first myth. So some people assume that when they change Virtio or extend it, this would break existing installed drivers or hypervisors. But that's not true, because the feature negotiation, it allows us to make changes with full backward and forward compatibility. Let's see how this works. So let's say we want to make a change to how a Virtio input device works. Say we want to add a new feature, multi-touch, for this input device. Okay, so we assign it, because whenever we make a guest visible change to device, that means we have to assign it a new feature bit. Okay, we assign bit 0 to our new multi-touch feature. And any input device implementing this will have to set this in the features register. So a new driver implementing multi-touch, it would set the corresponding bit in the driver features. Then combining device and driver features, it will still result in a bit 0 set when we end them together, right? So both device and driver can test this bit 0 to verify if they can support multi-touch or not. Okay, let's see what happens when we use an existing driver with the new device with this change. Now the driver will read the host features register with bit 0 set. But bit 0 is clear in the guest-supported feature mask. So that means it is cleared when we combine host and guest features. Thus, the driver writes out 0 into the driver features register on the device, and then it would work exactly as it's supposed to be. What about the device? The device looks at the bit in the device feature register that it has received from the guest. It will see that this driver has cleared bit 0. That means it's a guest without multi-touch support. It can now use this indication and switch, for example, to a compatibility mode, and it would behave just as expected by the old driver. Alternatively, if the device does not support compatibility mode, it could clear the features OK status register flag, and that would cause the driver to gracefully fail to attach the device. Yeah, that's OK. So we saw that a single device can be compatible with old and new drivers. What about the reverse? A new driver has a bit set in a supported feature mask. It will access an old device and detects a 0 in the device features register. As the result, we end up with 0 in the driver features register, indicating to the driver to disable multi-touch for the guest. So in a way, compatible with the old device. This works in the reverse direction as well. If there's a feature you want to drop, you can do this by clearing a bit in the device and driver feature bitmaps without affecting any other functionality. Okay, and in fact, this feature negotiation is working quite well. We have been able to transition from Virtio 0.9 to a completely different register layout with Virtio 1.0 without breaking any devices or drivers. The default was changed in QEMU 2.7. That was about a year ago, and so far there have been a few bugs but no major complaints about compatibility. So it is working quite well. We can say that we can make big interface changes here without breaking compatibility. Next myth. Is it true that any change that I want to make to a Virtio device requires me to write or change a full specification? You know, it's not completely wrong. You're absolutely encouraged to do that, but it shouldn't scare you away. It's not a top priority, at least not for all Virtio developers. So what are our priorities? Yes? Yes, the Oasis Virtio standard. Yes.
There's the design specification that would be the first step. That would be nice to have for Virtio as well, because it's still missing.
Yes, that's true. Okay, so our priorities are, we want code compatibility. We want to avoid conflicts between existing or past and future drivers and devices. Intellectual property rights compatibility. We need to allow others to implement compatible Virtio devices and drivers. And then there's interface compatibility. We want to allow different implementations to interoperate with each other. So how do you achieve code compatibility? For new devices, you just need to reserve a device ID. On top, this is a minimal patch to reserve a device ID, and this will guarantee that no other future Virtio driver will be bound to your device. If you are changing an existing device, then the minimal patch reserves just a feature bit. Here's an example for a balloon device. So this really is not much effort. It's like one line in each case. Don't be scared by that. How do you get this into the spec? You can download, you can git clone the specification, the LaTeX code, and you can change it. You can build it. It will build on Linux. It will also most likely build on Windows or Mac, I guess. What you do then is you subscribe to this mailing list, Virtio comment, send an empty email there, and you will be subscribed. And then you need to confirm your subscription. You send your patch to this mailing list, Virtio comments. If everyone's happy, there will be no replies, no comments. And then after a while, maybe after a week, you ask, send an email again, you ask for a vote, for a ballot. You put Michael Zirkin, he's the chair of the technical committee on CC, and then this vote will be open for another week. So it's about 2 weeks to get your change into the spec. Yeah, so we generally ask that we have an open source implementation draft at least available, and that you agree to the non-assertion mode of the Virtio spec. What do you do for this? You subscribe to the Virtio dev mailing list. You'll be asked to agree to these IPR rules, and then you send your patches to this mailing list. And many devices stop at this point. One example would be the Virtio GPU device. Next one is interface compatibility. This one is hard. So to interoperate with others, we really need good documentation. And in the ideal case, you would add a full description of new feature bits to the specification, of the new features to the specification. You don't have to be a member of the Virtio technical committee to do this. Some things to consider when you write the documentation. Please separate device and driver requirements in separative subsections. And only in those you use those keywords must, should, may, and so on. Ask for help if you don't know how to start. Try to avoid grammar and spelling mistakes as good as you can. So some examples at this stage would be Virtio crypto and Virtio input devices. Specification is still work in progress. Implementations are already in use. Now, if you maintain a part of the specification, then you could consider, or you should consider, joining the technical committee. Because that means you can also vote on spec changes. Membership is open for everyone. Maybe your employer is already a member of OASIS. Then there's no problem. There's no limitation to how many employees can take part there. So you might just be able to start to participate there. Okay, let's come to the next one. The Virtio spec, the current one, it seems to imply that the layout that was chosen is optimal from a cache utilization point of view. But is this really true? So to examine this assumption, let's say it is true. We will look at it. We'll look at it and get some background information. So Virtio does requests between host and guests by storing them in a Virtio data structure and shared memory. And this is what it looks like right now. So we have an available ring, we have a used ring, we have descriptors, and they are stored in a table. And we have these indices. The buffer address and the lengths, they are stored in these 16-byte descriptors. And all of them are stored in the table right there. If a buffer is not contiguous, you can chain them together by adding a flag to the descriptor. Where in the table this descriptor is put is up to the driver. A request is then identified by the head index, which is a 16-byte offset into this table. Head indices are stored in the available ring. To signal to the device which of these indices are valid, the driver will maintain an available index in shared memory as well. So after executing this request, the device will store this head index in the used ring. It also stores the length of the used part of the buffer. And then it will increment the used index value in shared memory and signal the driver by that. Okay. So fundamentally, we see that hosts and guests, they communicate by passing messages between CPUs using shared memory. And how do CPUs do that? So at a very low level, when one CPU accesses memory that is modified by another CPU as well, this will cause the CPUs to synchronize their caches. And they do that by exchanging cache coherence protocol messages. For example, some architectures, when a CPU accesses memory that was previously accessed by another CPU, that will also cause a cache miss. And the number of these messages that are exchanged and the misses, this will directly impact the communication latency we have here. So let's count cache misses with Virtio 1. Our queue consists of these 5 parts, these 5 data structures, and a buffer that moves between host and guest. Each of these parts is written and read at least once. So that implies 5 cache misses per buffer if we don't do batching. If we do batching, it looks a little bit better. So sometimes the driver will be able to submit a batch of multiple requests at once. And with this batching, the per buffer overhead is lower, as multiple buffers fit in a single cache line. With batch size set to 4, for example, a single 64-byte cache line holds 4 entries of each kind. So that gives us 5 misses per 4 buffers. Can we measure this overhead? So here's a small micro benchmark. It's from over a year ago. Michael did this back then. It's trying to measure the overhead of cache synchronization. And we measure the cache overhead by comparing the same micro benchmark when running on 2 CPUs with shared and separate memory caches. And you can see that most of the time in this benchmark is actually spent on cache synchronization, especially without batching. How can we reduce this overhead? So the information that we store in this Virtio data structure, it's spread over quite a few data structures. What if we would pack them together more tightly? And how about we just use one data structure, a single one? So we get rid of the available and the use string and the index structures completely. So, oh, by the way, this is something that we are looking into right now, we're discussing. So we get rid of available and use string and these index data fields. And we just use a descriptor ring. We make the guest write descriptors out in a descriptor ring order. And within each descriptor, we add 3 fields: an available bit, a used bit, and a descriptor ID. Okay, how to make buffers available to the host? The guest will write them out in the descriptors in a ring, and then it will flip the available bit. It implies that this is now okay for the host to consume this descriptor. Now the host can process those descriptors in any order. Each descriptor has an ID field, and after processing, the host will write the processed descriptor ID in the ring. Then it will flip the used bit. And this means that for the guest that this entry has been used. And it can now reuse it for a new buffer. So here's a special case, descriptor ring with 1 entry. Driver and device, they need to maintain internally, each of them, a single bit counter. It will start at 1 and we'll change it each time we start writing out descriptors at the beginning of the ring. This bit that's stored internally, it's passed as available and used bit in the descriptors. So let's assume that the ring is 0 initialized. On the first iteration over the ring, to mark the script as available. The available bit is set to 1. On the next iteration, it's set to 0, and so on. We change every time we cross the ring boundary in the first descriptor. So to mark the descriptor as used, the used bit is set to 1 on the first iteration and 0 on the second, and we continue doing this. This would be some pseudocode. What you can see is we read an entry and later we write it out. So best case here is the read will cause a cache miss and the write will be a cache hit. Worst case, both accesses cause a cache miss. Okay, the requests don't have to be used in order. The host can do it out of order. So this is an example where the guest made 9 entries available, and then it's starting out by using the 9th entry. Originally, both available and used flags are 0 initialized. It means the guest makes buffers available by changing the available flag from 0 to 1. Host writes the ID of the 9th buffer at the beginning of the ring, and then flips the used bit from 0 to 1. This will allow the guest to overwrite the entry next time it has to, and it will then flip the available back to 0. What does it mean for CPU caching? We get 2 to 4 misses per buffer with no batching, and half to 1 miss when batching up to 4 buffers. This seems better than what we have right now, even in the worst case. It seems better. We can do it differently too. So the descriptor ID, it's also useful for when the host processes the ring in order. Because sometimes the only meaningful information or the single useful bit of information for a descriptor is, has it been used? And in this case, we could also write reduce the number of memory writes, and thus also the amount of messages that need to be exchanged between CPUs. We do this by allowing it to just skip writing out some of those descriptors. The driver will then use the feature bit to detect we're processing in order and act accordingly. Okay. This is a comparison. We see that without batching, we managed to reduce the cache overhead almost by a factor of 2. With batching, the effect is a little bit smaller, but it's still very noticeable. And Michael also tested the shared cache performance of the new layout to measure the processing overhead. As you can see, it performs more or less the same as the old one. So better cache behavior is the main reason that the new layout is faster. This is an actual workload. Well, it's a test and a PVP setup with a packet generator on one system, and the device under test is another system running an actual guest. This is done with an initial prototype implementation, 64-byte packets. The improvement was with the old layout in the setup, 18.8 million packages per second, compared to 22.6 with the new layout. So this is using slow network cards, which means with larger packets we will just hit wire speed in the setup. And I didn't get around to measure bigger frame sizes with faster cards yet. That should happen very soon. So I think we can say that the Virtio layout is not really optimal right now for host-to-guest communication. But the current discussion that we're having, these experiments, is to be able to work on that, on fixing it. Okay. I think I'm actually skipping this one. Let's go to number 2. So usually our Virtio queues, they have to be a power of 2. Why not, right? Power of 2 is nice round numbers. So why not? Also cache utilization. Let's take, for example, this CPU with a 32K and 8-weight associative cache. Say we have a ring with 1K entries, and this will occupy 16K kilobytes. So that means 4 of the 8 ways are spent. Now consider a networking device with 2 rings for transmit and receive respectively. If we attempt to use this device for 2-way communication ring access, this will push all other data out of the cache. Now, if we remove this requirement for power of 2, we could make it a little bit smaller. Say we give it 768 entries per ring. So that would leave us with at least 1 cache line free for something else to do. Okay, but isn't power of 2 nicer to code? Doesn't it make our code more compact and more beautiful? Well, the difference is not this big. So this is an example of how to find the next valid descriptor with or without this assumption of power of 2 ring size. Yes, power of 2 is a little bit more concise, but only slightly. Good. Coming to the next slide. So from a guest point of view, Virtio devices, they tend to be PCI devices. And it seems natural to assume that things just work if you implement a Virtio device in hardware and pass it through to the guest, things will just work, right? It's mostly true. But sometimes we found out that hardware devices require different optimizations from a host-guest communication point of view. So for example, software has to process descriptors one by one. Hardware could go grab a bunch of them and process them in parallel, right? So that would be nice, except the device generally does not know ahead of time how many descriptors are available. And to enable this optimization, driver kick must give the device a hint as to how many descriptors are available for processing. The device then would then use this hint to fetch and start processing multiple descriptors at once. That's one thing. Another one, when we think about hardware, writes are expensive. So another optimization would be writing out used descriptors, but each device, right, means some overhead. So a PCI Express payload is a full D word, and that should be expensive. We have a solution for when processing happens in order. I mentioned it earlier. Similar to the software case, what we're considering now in this discussion is actually allowing devices to skip writing out some used descriptors. That means the driver will use a feature bit to detect the fact that rings are processed in order, and then it will simply assume that any skipped descriptors have been used. So with this, I already come to my last slide. Virtio 1.1 shapes up to be a big one, a big release. Main focus is hardware performance for hardware offloads and performance in general for software as well, obviously. Contribution is open. Don't be shied away by the spec or ACES or anything. It's really not this complicated. It would be good to have you as a part of the discussion. We will continue with some more implementation. There's a lot to be done. We will also continue with benchmarking. And tomorrow, as a BOF session, we will have one especially for this topic. So if you're interested in this, join us tomorrow. I think it will be announced when and where they start. So look at the schedule, and then we'll meet there. Okay, that's it from my side. Are there any questions?
Hello, thanks. Back to my initial mentioning in the beginning, and I see here this very nice line here, join the fun. You on the slide about, hey, don't be afraid to change the standard, the specification, you know, yeah. It's more of a standard. So, okay, but actually there's one other step. I mentioned the design specification, and I see this I worked with Virtio from 2015. I had to create a bit of custom driver for high performance computing, proof of concept, sharing memory resources between guests. And my first task was spent a month and a half to research, to actually understand how everything works. There was not a single well-written document. And yeah, and the other attendees are already laughing because we all are aware of this issue. There is no design specification. And even back then, I heard this, hey, join us, work with us, you know, from Linaro also. And I'm thinking, yeah, sure, a lot of people are interested, but the barrier, it's not about that people don't have motivation, they are not interested in paravirtualization. It's just that when they go there, what they find is a mailing list full of interesting information, people open to talk. But you know, it would be so much easier if we can just get some kind of a design specification, yes. Just the baseline, so people can really enter a bit more easier. And then you get a lot of more contribution. Yeah. So maybe this would be something part of the thinking about it.
Yes,
and do you see anything about this forming, planning people? Because writing documentation, sure, it's not fun, but really, yes. You know, design specification, it's not the full technical documentation, just the really architecture level.
I completely agree with you. It's the barrier if you just read the spec and you're supposed to understand it or implement it, it is not easy. There should be a document, as you say, that outlines how it works, where it starts, in a more normal language.
Yeah, because
and somebody needs to write that. I agree.
Of course, someone needs to dedicate time and pay someone to say, hey, you're working with Virtio. Let us give you 2 weeks or 1 month just to actually your accumulated knowledge. Just make it in black and white, just the basic, just a paragraph. Because what was the barrier for me in 2015? It was just simply, I had to study the code, which is fine, but it would be so much easier if I could just read the code. Hey, I have a question about how actually this works. Okay, here's a paragraph, 2-3 lines, really. You know, that's all I needed.
Yes.
So, and I too, as you can see, I didn't write it because at the time, the client, the company I was working for, yeah, we don't want to pay you to write the design specification for Virtio. We want you to implement this solution for us, design it, write the design specification for the solution. But wait, there's no time, just do the solution.
Yes.
Yeah, you know what I'm talking about. So, do you see anything of this happening in the near future?
I really want it to happen. I don't see that it has started yet. Not yet. Try the other one.
Hi. Yeah, good. So it would be very useful if we could also get some hardware examples. Currently, the only one I've seen is the Xeon Phi chip and the many integrated cores, and that's not really easily understandable.
So what kind of examples? I didn't get that.
So when you want to connect an external hardware device, actually, so the Xeon Phi was a PCIe connected device that then leveraged Virtio to give you direct connections, well, not point-to-point, just the serial ones, but it gave you networking and block devices, and it would really help if there could be more of these devices. Okay. Some of us really want to use Virtio just for hardware cross-connection as well, not just between guests and hypervisors.
Okay, good. Yeah, I'll take that with me.
Thanks.
Hello, Christophe de Dinchin. So you talked a lot about the effects of cache misses, and so this seems to be an important consideration for performance. What kind of efforts have been put to try to preserve some kind of per CPU locality, making sure, for instance, that the driver and the emulation run on the same CPU? Things like maybe spreading out, having one index per CPU, per physical CPU, and trying to look first if I have stuff to do on my CPU, and only otherwise look at the others to avoid thrashing the cache of the other guys.
Can you repeat it?
So say I have a 4 CPU system. One of the issues I get is if I write on my side, I'm going to invalidate that cache line for all the other CPUs.
Yeah.
Right, so that slows them down looking at it. So if I'm writing first, trying to make sure that I write only for my own stuff that would be emulated on the same CPU on the other side, then I minimize this effect. And if I only look at the other CPU's memory, once I'm sure that I have nothing to do on my own CPU, then I could minimize this effect. That would sort of imply instead of having one structure, I have 4 of them, and I look only at mine first, and then I look at the others.
Yeah, maybe. Just think about it. I'm not sure. Stefan?
Thank you. So just as a follow-up to that, I mean, some of the Virtio devices are multi-queue, and they are designed for that. But the thing to keep in mind is that if the virtual machine accesses one of these queues, normally when a CPU accesses hardware, you don't want the CPU to be paused while the device is running. And so it's the same thing with Virtio. We don't want to incur a lot of steal time if the device emulation is happening on the host. So I think we're still going to have threads because you probably don't want to do everything synchronously when the CPU traps. So I guess, yeah, so those are the constraints, I think.
Yeah, so that's not what I was suggesting. I was really more thinking about trying to make sure that if you're running, for instance, emulation on CPU 1, you try to first pick workloads that were written by CPU 1, and only then look at the queues that are on the other guys, and I think you can do that.
So then the answer is, as Stefan was saying, that you don't want to run emulation on the same CPU, so that won't happen. But what you can do is to make sure that your emulation at least runs on the same NUMA node as the device, so that at least the cache misses are not that expensive. And to do that, for example, we have support for multiple PCI expander bridges, so that you can say that a particular device has an affinity to a particular NUMA node, and then it becomes a configuration problem to put the I/O threads and the CPU threads on the same NUMA node and have everything matching, even potentially up to the hardware level, so that the I/O thread runs on the same NUMA node as the physical network card, for example. Does this answer the question?
Okay. Anyone else?
Yeah.
Over there, okay.
Go on.
You have a mic, okay.
I'm still trying to get my head around this new descriptor model you have, so I'm not sure if this is obvious or not. On Virtio 1.0, you have a situation where a device may consume an index from the avail ring, and it's processing that descriptor. And because requests can be completed out of order, the avail ring can continue to be populated, the device can continue to consume this, and
yes.
the avail ring can just loop around many, many times. At that point, just by looking at these data structures, you're not able to tell what's still outstanding.
Yeah, so that's...
Is this something that this model would address?
Yes, so we're talking about the case when we wrap before everything was used.
And there is something outstanding.
And there's something else still standing. So this is covered by this. So the driver has to make sure that the available bit is not equal to the used bit. And this is how you could tell. And keep in mind that the bit will be flipped as well. But not for, if you skipped some of those descriptors, for those descriptors, nobody took care of that. That's the case. That's what you're talking about.
Right.
So in this case, next time, so we wrapped around, and I think it's on my slide. the driver needs to make sure that the available and the used bit, they can't be, can have the same value. Is that?
Yeah, which means it's still pending in some way.
Yes.
Right.
But then when it wants to write to this descriptor, it will notice that so its internal value has flipped because we crossed the ring border.
Right.
And then and it sees this descriptor that wasn't used before, and it still has the old value. So let's say now our counter is 1 and it's still 0. That's how it would tell.
Okay. What's the size of your ID field?
Some 2 bytes, I think.
Right. That's not a problem if that wraps as well.
No, I don't think so. Okay, I think this was the last question, end of the talk. If there's anything else, please consider coming to the BOF tomorrow. Thank you.